Let me briefly introduce today's speaker. Today's speaker is Takashi Toma-san from Kanazawa University. He received a PhD from Kanazawa University at 2012, and after that he experienced a postdoc in Durham University and LPT in Orsay, and the Technical University of Munich, TUM, and Kyoto University, and after that McGill University. And from 2020, he has been an associate professor in Kanazawa University. So today he's going to talk about the direct detection of pseudo-Nambu-Goldstone dark matter with light mediator. So Thomas-san, please start.
Thank you very much for introduction, and thank you very much for the invitation to this nice seminar. I'm Takashi Toma from Kanazawa University. Maybe you don't know the location of Kanazawa University, so here I put a small map here. Kanazawa is located here. This is between Osaka and Tokyo, north area. So if you come to, if you have chance to come to Japan, please visit Kanazawa. There are very nice Japanese things like Japanese seafood and Japanese old culture, something like that. So anyway, today I'd like to talk about this topic, pseudo-Nambu-Goldstone dark matter with light mediator. This talk is based on these papers, and the collaborators, there are a lot of collaborators here. Christian Gross, he's a postdoc at Pisa University in Italy. Koji Ishiwata, he's associate professor at Kanazawa University. Oleg Lebedek is a professor at Helsinki University. And Yoshihiko Abe, he's a PhD student, final year PhD student at Kyoto University. And he will move to Wisconsin University after getting a PhD, supported by JSPS fellowship. And Koji Tsumura is associate professor at Kyushu University. And Naoki Yamatsu, he's also in Kyushu University. This is outline my talk. First, in the introduction, I briefly review about dark matter, in particular, WIMP dark matter. Maybe you already know about WIMP dark matter, but let me briefly review about this. And after that, I will talk about pseudo-Nambu-Goldstone dark matter. This is written like this, Pngb dark matter. And yeah, in this model, I calculate direct detection cross-section at 3 level and 1 loop level. And then this is for the heavy mediator case, basically. And after that, I will move to the Pngb dark matter with the light mediator case. And then I summarize my talk. As you know, dark matter should exist in our universe. There are a lot of experimental evidence of dark matter, like rotation curves of spiral galaxy, like this. From CMB observation, we know about 27% of total energy density of the universe is occupied by dark matter component. And dark matter is introduced to give additional source of gravitational interaction. And this is the simulation of the structure formation of the universe. In order to get this kind of filament structures, we should introduce dark matter component as an additional source of gravitational interactions. And this is a picture of a collision of Barrett cluster. The red part corresponds to the usual matter collide, and they emit X-rays, strong X-rays. And this blue part corresponds to the dark matter collision, and this is reconstructed by weak gravitational lensing effect. So from this picture, we can see dark matter interaction, self-interaction is much weaker than the normal matter because we can see the blue part can pass through with each other. So from this experimental evidence, the existence of dark matter is crucial, but we don't know much about dark matter. So this is a list of the nature of dark matter we have already known. First, dark matter should be stable, or at least dark matter lifetime should be longer than the age of the universe. Otherwise, the dark matter can decay, and there is no dark matter in the current universe. The second, dark matter should be electronically neutral, or maybe dark matter may have a very small electric charge, order of 10 to minus 10 or something. And third, dark matter should occupy 27% of total energy density in the universe. This comes from a CMB observation, as I said before. And dark matter should have gravitational interactions to explain the spiral galaxy rotation curve. And dark matter should be also non-relativistic. This means a cold dark matter in order to reproduce the structure formation of the universe. So theoretically, there are many dark matter candidates like WIMP, FIMP, SHIMP, action, stellar neutrino, primordial black holes, and so on. WIMP means a weakly interacting massive particle. This is a traditional dark matter candidate. And there are some other dark matter candidates, but in this talk, I'd like to focus on traditional WIMP dark matter candidates. So this is the n-body simulation. If you consider cold dark matter, this means non-relativistic dark matter. You can see this filament structure. This is matches with this structure formation. So dark matter should be cold. So probably you already know about the WIMP production and experimental status, but let me briefly review. WIMP number density follows this Boltzmann equation in the early universe. Nk is the number density of dark matter. H is Hubble parameter. And sigma V, this is annihilation cross section of dark matter. Two dark matter particles going to annihilate to the standard model particles. And this NKEQ is number density of dark matter in the thermal bath. This Boltzmann equation can be rewritten in terms of dimensionless parameters like X and capital Y, like this. X is defined by mass of dark matter divided by temperature of the universe. And capital Y is defined by number density of dark matter divided by entropy density. So this equation can be solved, and this is a typical behavior of the solution. So x-axis is this basically time evolution, and the y-axis is yield capital Y. So at first, dark matter number density follows the equilibrium number density because the annihilation and the inverse annihilation can occur, and they are thermal equilibrium. But around here, dark matter annihilation freezes out, and after that, dark matter annihilation doesn't happen anymore. So the number density of dark matter is almost fixed like this, depending on the cross section. This one. So for smaller, larger cross section, you can see the final abundance of dark matter is smaller. So the final abundance is almost determined by one parameter, this annihilation cross section. There's also a very small dependence on dark matter mass, but just logarithmic dependence. So we can ignore the mass dependence. So in that case, the number density, energy density of dark matter, omega h square, is very roughly given by this formula. So this is inversely proportional to annihilation cross section. So this should be very roughly 0.1 to be consistent with Planck collaboration experimental data. So in order to get to this value, we can see the typical value of annihilation cross section is 10 to the minus 9 giga-electron volt inverse squared. Or with different unit, this corresponds to 10 to the minus 26 centimeter cubed per second. This is a typical value of the annihilation cross section of WIMP dark matter. So WIMP basically it can be researched by several experimental techniques through indirect detection, direct detection, and collider search through this crossing symmetry. So for collider search, this is an example plot obtained from Atlas collaboration. So this is for SUJI supersymmetric dark matter model. So neutralino is lightest neutralino is identified as WIMP dark matter. And there's also chargino and second, third component of neutralinos. So from this plot, we can see this lower region is also already excluded by collider search. So in order to avoid this collider experimental constraint, we can see neutralino mass is almost degenerate with the other particles. Around here is also, around here, this parameter space is allowed. So this is the status of indirect detection. These plots are taken from Fermi-Lat gamma ray observation from dwarf spheroidal galaxies. Depending on dark matter annihilation channel, BB bar and tau tau, a lot of gamma rays are emitted from these final state particles. So depending on these annihilation channels, we can get the strong constraint on the dark matter annihilation cross section. X-axis is dark matter mass. So the upper region, this region is already excluded by this BB bar and tau tau bar. So from and this dotted horizontal line, this is the cross section which is required to reproduce the thermal relic abundance of dark matter. So we can see from this plot very roughly order less than order 100 GeV of dark matter mass is already excluded by indirect detection experiments. If dark matter annihilation channels is dominantly going to BB bar or tau tau bar. So this depends on dark matter annihilation channel. So this is the direct detection. The right plot is a xenon-1-ton experiment. This is the upper bound obtained by xenon-1-ton experiment. The upper region is already excluded. And in very recently, this bound has been updated by Panda X photon collaboration. This red line is the current strongest constraint for direct detection obtained by Panda X photon collaboration. So in particular, this direct detection constraint is very strong. This experimental status for WIMP dark matter may imply that the interactions between dark matter, WIMP dark matter, and the standard model particles are very weak. So this motivates us to consider non-WIMP dark matter like FIMP, SIMP. FIMP means feebly interacting massive particles, very weakly interact with the standard model particles, or strongly interacting massive particles, and so on, action, and so on. But in this talk, I still would like to focus on the kind of WIMP dark matter. So the point is how to avoid this very strong constraint from direct detection. So this can be done by considering pseudo-Nambu-Goldstone dark matter. This particle can be identified as WIMP in the next slides.
Takashi, sorry. Yeah. So in your slide on the left-hand side, do you know why the general quantum bound stops at 1 TeV?
This one.
Yes. Because they don't know. General quantum shows only up to that mass. Or?
Yeah, they cut here 1 TeV. Yeah. Actually, I don't know. But
in principle, it can continue.
Yeah. Basically, this just you can extrapolate. Yeah.
Right. Parallel to this Panda X.
Yeah. I think
it can continue. Like
okay.
100 TeV, I don't know.
100 TeV. I think
unitarity.
You can extrapolate. I think. But
if I don't know, if you can, I mean, these days people try to get thermal dark matter many different ways. So in principle, just we can put some phenomenological, experimental bound independent of dark matter masses.
Yeah.
Maybe we don't have to confine ourselves below unitarity bound. Maybe we can still extend it, right? I don't know if dark matter is too heavy, direct detection bound, whether direct detection bound is affected or not. We could change it just to, it's not just to simply extrapolating.
Yeah, basically, I think you can simply extrapolate. But I don't know if dark matter mass is very high, very heavy. This means the recoil energy when collide with nucleon. This recoil energy can be much larger. So this may affect the constraint. I don't know.
I think if dark matter mass is too large, then reduced mass is just a nucleus mass. So and for fixed relative velocity between nucleus and dark matter, so the recoil energy is kind of limited by this just a reduced mass. So I think still you still see a WIMP-like signal in the limit of heavy dark matter, but just to as you know, I mean this because the abundance decreases, number of dark matter particles decreases for heavy dark matter. This is how they extrapolating this bound to large masses. But I'm just wondering if dark matter is too heavy. Is there any thing. I mean, just one collision for particle when the dark matter comes in, and it hits one nucleus at one time, and from that they kind of sum over all the nucleus in the target, and then they have some exposure for 1 year, something like that, 1 ton, something like that, photon. So it's kind of averaged quantity in the end, and then they expect some number of events. So that is based on the assumption that the dark matter hit nucleus at once when it comes in. But if I don't know if there are some multiple scattering for one dark matter, maybe the events could depend on the multiple scattering or some, I don't know. This people ask such a question, but I don't hear any clear answer to this one. So I don't know whether the limit becomes stronger than we expected. Probably because you are generating more events. So instead of keep increasing, the limit keep increasing. Maybe, I don't know, it should, I mean, this becomes stronger at some point. I don't know. Yeah, just to, I don't know if you find some answer to this. Maybe
I didn't understand why you expect the curve should stronger.
Because when it comes in, I think it scatter multiple times.
Multiple times.
I mean, very heavy guy. Just most of time, I think the dark matter pass through in the target.
Yeah.
But I don't know. It scatter many times with the nucleus. I don't know. That's my just a simple question, naive question.
Yeah, that's an interesting possibility. Yeah.
There is some recoil, but most of the time the dark matter goes through because it is too heavy. There is the recoil energy deposited into nucleus limited by like a nucleus mass times relative velocity square. But we are sure about that for single collision. But if you have a multiple scattering, as dark matter pass through, there might be a series of cascade. I don't know. But I don't know. Maybe dark matter lose energy. In most cases, dark matter lose kinetic energy for single collision. But if it doesn't lose all the energy, because dark matter start with a large kinetic energy, right? The dark matter mass is like 100 TeV times velocity scale. So it started with a very large energy, but it deposits very small amount of energy, right? It's like nucleus mass is 100 GeV something, 130 something in the case of xenon. Then you started with a very large energy, but mostly it passed through without losing much of energy. Suppose it loses energy, it loses energy somehow due to multiple scatterings, then maybe the events that you expect might be greater than naively thought. So this kind of thing that one can ask, right?
Yeah. But if you
go ahead, sorry.
Sorry?
I'm sorry, never mind. Go ahead.
If you have a multi-scattering events, you need a much more cross-section, maybe. That is also the excluded.
Yeah, it also depends on the cross-section.
Yeah.
Yes. The cross-section also, but yeah, I don't know. The cross-section also decreases, right? By dark matter mass square, or it depends on the mediator type. Without such a prejudice, suppose dark matter, such a heavy dark matter could be produced for some reason, and you just focused on the interaction. And then, of course, there might be some unitarity bound on the strengths, but I don't know. But it'll be interesting to think about.
That's interesting. Yeah.
But if it how to say, if it the chance to fact-wise collision is quite, I think it is quite small, because it must be, the chance must be proportional to the second order of coupling. How to say? Hit. The chance to hit twice must be, in my opinion, it should be twice of.
I'm not talking about higher order processes. I'm talking about still 3-level processes. But
3-level?
3-level processes. But normally what people do is for single scattering, dark matter lose kinetic energy completely, and another dark matter comes in, lose kinetic energy, and another particle lose kinetic energy, something like that. But if one particle comes in, lose kinetic energy through multiple scatterings. I mean, it scatters once, but it doesn't lose all the kinetic energy. And scatter with another nucleus, lose kinetic energy, for instance. I'm talking about this kind of situation. At each scattering, you have a 3-level processes.
I got it.
So yeah, but yeah, please go on. I think otherwise you cannot finish.
So let me continue. I'd like to consider Pngb dark matter. This model is basically very simple. We just introduce a complex scalar field, capital S, which is written like this, small s and chi. This chi is identified as a dark matter, pseudo-Nambu-Goldstone dark matter. And we assume global U1 symmetry. So this scalar potential is invariant under global U1 symmetry. But in addition, we would like to we add only one soft breaking mass parameter, this term. This is important to give a mass for Goldstone boson here, this chi. Otherwise, this chi is completely massless because of this global U1 symmetry. And this Higgs, this is a Higgs doublet in the standard model. This breaks spontaneously electroweak symmetry breaking. And this capital S also spontaneously breaks global U1 symmetry. So after getting BEPs, V and VS, they can be rewritten in terms of CP even component and CP odd component. And the CP even components mix with each other, phi and S, and this one and this one. They written in terms of mass eigenstates H1 and H2, and H1 is corresponding to the standard model Higgs, standard model like Higgs with 125 GeV mass, and H2 is a second Higgs, and this sin theta is a mixing angle between phi and S. This is a very roughly constrained less than 0.3 by electroweak pressure test and H2 direct search. This is a constraint on the sin theta. This plot taken from this paper, and the colored regions are already excluded. So, so sine theta should be less than, very roughly less than 0.3 and here, or maybe less than 0.1 if MH2 is less than 125 GeV. So in this model, chi, this one can be a dark matter candidate, and this mass is given by just the soft breaking parameter, this one, this parameter. And this Pngb can be stable due to the CP symmetry in the scalar potential. And this scalar potential can be rewritten in terms of mass eigenstates, chi, H1 and H2, like this. In particular, this cubic coupling, chi H1 and chi H2, these are important to calculate direct detection rate. And also standard model coupling also modified like this. The interaction with H1 and H2. Actually, in this model, there is a domain wall problem because this global, this scalar potential has a discrete Z2 symmetry. And this Z2 symmetry is spontaneously broken by the vacuum expectation value of S. So this may distort the CMB, but there are some solutions to solve this problem. First, we may be able to say this Pngb dark matter model is an effective model at low energy, and this model can be this model can be induced from the high energy UV complete model. And there's possibilities for solutions like decay before BBN or low energy inflation after Z2 spontaneous symmetry breaking. So in particular, this first option, we can construct a concrete model. So this is an example. Here we extended the model with gauged U1B minus L symmetry. So there's also additional field, phi. This is a kind of Majoron field. And so under this charge assignment, we can have cubic coupling here, SS phi star. So after getting BEP of phi, we can see this term gives a soft breaking term at low energy. And there are also 3 right-handed neutrinos here. These are required to cancel gauge anomalies. And because of this, the existence of the right-handed neutrinos, we can also keep the small neutrino masses through canonical seesaw mechanism. So anyway, in the effective, I mean, in this Pngb model, let's calculate direct detection rate. The elastic scattering between dark matter and the nucleon can be induced by this 3-level coupling, mediated by H1 and H2. And scattering amplitude is proportional to this factor. Q square is transfer momentum, and H1 mass and H2 mass. So because this Q square is much smaller than MH1 and MH2, we can expand this scattering amplitude, and then we can get this one. And you can see in the zero limit of transfer momentum, the scattering amplitude goes to 0. This result can be understood due to the nature of pseudo-Nambu-Goldstone dark matter. So if we write the Lagrangian with this non-linear representation of capital S, we can easily understand the vanishing scattering amplitude, because the Lagrangian can be given like this in this notation. And then this cubic term S chi is corresponding to this here, this coupling. And from this interaction, we can see the amplitude is proportional to P1 minus P2 squared. This corresponds to the transfer momentum here. So in the non-relativistic limit, we can see the scattering amplitude goes to 0. This is because, as I said, due to the nature of Goldstone dark matter. And in this model, we can have only 4 independent parameters. We choose dark matter mass, second Higgs mass, sin theta mixing angle, and web of S. Or maybe you can take lambda S instead of VS as independent parameters. And so this is at the 3-level case. As I said, at the 3-level, the scattering amplitude goes to 0 in the non-relativistic limit. But at the 1 loop level, there is a finite value of the cross-section, elastic cross-section between dark matter and the nucleon. And at the 1 loop level, there are a lot of diagrams like this: self-energy correction, vertex correction, and box triangle corrections. Basically, these box and triangle corrections are smaller than the other diagrams because there are 2 Yukawa couplings here. So, including 1 loop level calculation, this is a parameter space. X-axis is dark matter mass, and y-axis is Webb ratio, V over Vs. And the upper region is excluded by perturbative unitarity bound of lambda S, because this Webb ratio, V over Vs, is basically roughly corresponds to square root of lambda S. So the upper region is excluded by unitarity bound. And here, a violet region is also excluded by Higgs invisible decay. The branching ratio of Higgs invisible decay should be less than roughly 20%. And this red curve corresponds to the parameter space, which can reproduce the correct relic abundance by thermal production mechanism. There are 2 resonances here, H1 resonance and H2 resonance here. And this green curve corresponds to the future sensitivity of direct detection experiment given by Darwin. So only a partial parameter space, very limited parameter space can be checked by a future Darwin experiment. And there is no direct detection constraint at the current from the current observations. So this is the case of sin theta equal to 0.1, and depending on sin theta, a bit parameter space change like this. Yeah, basically a very limited parameter space can be checked by future direct detection experiments.
So currently there is no bound from Genoa one-tone
No bound
Indirect. No.
at one loop level. Yeah.
So you have velocity suppression in the direct detection. And if you make the 90-degree rotation, you have annihilation with the same couplings. You have also velocity suppression, also annihilation, right?
For annihilation, there is no suppression.
No suppression, no cancellation.
No. Because the transfer momentum is much bigger. Because the transfer momentum is basically 4 times the dark matter mass squared.
So I see. So 4 times, okay. So center mass energy.
Center
S channel.
Center.
I see.
Yeah.
So Q square is replaced by the center mass energy in the S channel.
Yeah.
Okay, I see. I see no velocity suppression. Okay.
So
I have a very naive question. I just wonder MK, this is the mass of pseudo-Nambu-Goldstone, right?
Yeah.
The mass is can be arbitrarily, how to say, large.
In our analysis, dark matter mass is taken to be arbitrary.
I'm just confused with the word soft breaking, because naively I thought the explicit breaking term should be small, but is there any constraint or?
I think that is a naive assumption that dark matter mass is much smaller than the mediator mass, because dark matter mass comes from soft breaking term. But for example, if we extend the model with the UV completion, we can have this cubic term, and the soft breaking term comes from this term. And if this vacuum expectation value of phi is much bigger than the web of S, we can naively expect dark matter mass MK is much larger than the other masses. So depending on model building, I think dark matter mass can be large or small.
Okay, so you mentioned there's no restriction in your work.
Yeah.
I mean, there's no restriction on the upper bound of MK.
No restriction.
Okay. I see. Thank you.
Yeah.
I have several questions on the same slide. Actually, I think that I had a similar question when you give a talk. But can you go back to the same slide?
Which one?
On this model. So I have 2 questions. One is the this renormalizable interaction for S square. So phi, the vacuum expectation value of phi is very large, right?
Yeah.
So you need the small mu, right? Small mu c.
Yeah.
So
yes.
So my question is it possible to, instead of renormalizable operator, is it possible to introduce higher dimensional operator to get small MK, even in the presence of high scale symmetry breaking? And the second question is about the stability of dark matter. So you said the stability is guaranteed because of this CP conservations, S to S going to S theta, right?
Yeah.
It seems that it's not guaranteed in this potential from the beginning. Somehow you need to impose another
in this UV completion, actually dark matter is destabilized by the interaction with the fermion
I see.
So yeah, dark matter can decay in this UV compression.
Okay.
So basically, this vacuum expectation wave of phi should be much larger, about the Gato scale or something. Otherwise, dark matter lifetime should be shortened. Yeah.
See. You have some. I see. So, and then I mean, for technical, maybe you need. This is a kind of soft breaking term from the point of view for global U1, like a global U1 in the sense for this Goldstone. Goldstone, the pseudo-Goldstone is the consequence of spontaneous broken global symmetry. So you want to break the global symmetry. You want to break the global symmetry by small amount. But but I understand. But somehow, does it also depends on the charge assignment, like B minus L, such that this, like for instance, phi star S square is forbidden, and you can go to higher order interaction, like
basically, I think you can do it. But in this project, we wanted to construct renormalizable level completion, UV completion. So that's why we considered cubic coupling.
I understand, but I think it's might be more natural to think about higher dimensional because we want to explain small parameter. So it's not if you have a 3-level interaction, just a 3-level kind of mediator, kind of you are thinking of 3-level mediator. But if you have some heavy mediator in between, then maybe you may have a natural suppression, and then the heavy mediator might be the suppression scale for the higher dimensional operator. Although I think that you need more structure, but I think it will be interesting to think about the possibility. Although it's not minimal, I agree. But
that's another option. Yeah, I think.
So that I think we need to collaborate. Okay. Let's please go on.
So in the previous slide, we considered the heavy mediator case or comparable dark matter mass mediator case. So in the next, I'd like to consider light mediator case, light mediator H2. Because as I said, for example, in the UV complete model, basically naively we can get a large dark matter mass, which is much larger than MH2. So we would like to do this possibility. So in this case, dark matter main annihilation channel is given by H2H2, this one. And there are 4 kinds of 3-level annihilation channels diagrams. And the full expression of the annihilation cross-section is much complicated, but this can be simplified by assuming that the sin theta mixing angle is much smaller than order 1, and MH2 is much smaller than MH1. So in that case, annihilation cross-section is simplified like this. And there are also the other channels like WW, ZZ, FF bar, H1, H1, and H1, H2. But these channels are all the channels are proportional to sin theta, small mixing angle. So this is negligible compared to this H2H2 channel. And here we focus on the mass range of MH2 from 20 MeV to 200 MeV. because the right MH2 is already excluded to BBN constraint. And for larger dark matter case, we cannot get direct detection rate as we explain later. So we focus on this mass range. And this is the current constraints for mixing angle as a function of MH2. So we focus on this parameter space. Upper region and lower region are already excluded by some BBN supernova experiment and K-meson decay or something. So the sin theta should be in this range, 2 times 10 to the minus 5 to 10 to the minus 4, rather limited parameter space. So these cubic couplings are important to consider to calculate H1 decay into H2, H2. This coupling is important hereafter. So in that case, light mediator case, there are some indirect detection bounds on annihilation cross-section because dark matter annihilate into H2, H2, and H2 can decay into E plus minus. This mode can be constrained by AMS indirect detection observation, and gamma ray. Gamma rays are also emitted from E plus minus, and the CMB observation by Planck collaboration. So this plot is taken from this reference. Here they did model independent analysis for these 3 constraints for cascade decay, one-step cascade decay. So this is the upper bound on annihilation cross-section for Chi-Chi into H2, H2. So depending on parameter space, the dark matter mass, AMS gives the strongest bound, or Planck CMB observation gives the strongest bound. But direct gamma ray observation doesn't give strongest bound for this channel. And for Higgs decay, Higgs H1 can decay into H2, H2 and Chi-Chi because H2 is much smaller than H1 mass. So these can be can contribute to Higgs invisible decay because H2 is also long-lived. So the branching ratio of invisible decay should be less than order 0.11, 11%. So basically, the large coupling lambda S, order 1 coupling is excluded by this Higgs invisible decay constraint. So next, I will calculate event rate for direct detection. The relevant diagram is the same as before up to 3 level. But here, the situation is different because the transfer momentum Q square can be same order with MH2. So in that case, we cannot simply take zero limit of dark matter velocity. So if this transfer momentum is larger than MH2, we can have a finite value of differential cross-section. And this F is a form factor of the nucleus. This is basically expressed by a exponential factor with recoil energy ER. So the event rate, differential event rate, this one, DRTE, this is given by the differential integration of differential cross-section times velocity of dark matter. And this F is a Maxwell-Boltzmann distribution function of dark matter velocity. And then this is the left panel is the we translated the xenon-1 bound in terms of number of event, total event R. We integrated this one in terms of ER. So we get this bound. The outer region is already excluded. So, and we took into account detector efficiency like this. This is a detector efficiency of xenon-1 experiment. So next, this is an energy spectrum of Pngb dark matter. The violet lines corresponds to Pngb dark matter. And as a reference, we also put scalar normal WIMP dark matter, these green lines. So you can see the energy spectrum as a function of recoil energy for Pngb dark matter can be differentiated from normal scalar WIMP dark matter, so like this. So this difference may be important to discriminate the Pngb dark matter and the other WIMP dark matter. This difference comes from the different momentum dependence on the differential cross-section like this. And there's also a similar work worked by Thomas Hamby, and they considered momentum dependent differential cross-section, which is different from the Pngb dark matter case. And they also obtained the different spectrum compared to normal WIMP dark matter case. So as I said, this different spectrum can be used to discriminate the types of WIMP dark matter. But one note is that the similar spectrum with Pngb dark matter spectrum may be induced by different mechanisms like inelastic scattering. In this case, Chi1 is a ground state of dark matter. This can this can scatter with nuclei, and then excited state of dark matter Chi2 is produced. In this inelastic scattering event, the energy spectrum is typically goes like this, the red curve. This is similar to Pngb case. So maybe this becomes hard to discriminate inelastic scattering event and Pngb dark matter. So finally, I show some plots. Here we plotted a parameter space in the plane of lambda s and dark matter mass. In the case of sine theta equals 10 to minus 4. So colored regions are already excluded by Higgs decay, xenon-1 experiment, and AMS observation. This red curve is the parameter space which can reproduce correct relic abundance by thermal production mechanism. So from these plots, we can see only the resonance region of Higgs resonance region can evade all the constraints. And some parameter space here can checked by future sensitivity of xenon n-ton experiment. So this is a case of light mediator 30 MeV, 60 MeV, and 100 MeV, 200 MeV. So for heavier mediator case, like 100 MeV or 200 MeV, the Higgs xenon 1-ton experiment, experimental constraints can be relaxed because, as I said, for light mediator, we can get large event rate. So this is for the another parameter set. Sin theta equals 3 times 10 to minus 5. So this is the same plot, but important point is here we have allowed parameter space different from Higgs resonance here. So, and this around here parameter space can be checked by future sensitivity of direct detection experiment. So this is for heavier mediator case, like 100 MeV or 200 MeV. So in that case, more parameter space can be allowed like this, but this parameter space cannot be checked by a xenon n-ton collaboration, future sensitivity. So this is a summary of my talk. As I said, thermal WIMP dark matter is strongly constrained by several experiments. In particular, direct detection experiments give very strong constraint on the elastic scattering between dark matter and nucleon. But that constraint can be naturally evaded by constraining Pngb dark matter. And we calculated the elastic scattering cross-section at the 3 level and 1 loop level. And we found elastic scattering cross-section with nucleon at the 1 loop level. It's roughly order 10 to minus 48 centimeters squared. This is the maximum value. And the very partial parameter space can be checked by future direct detection experiments like Darwin. And the next, we consider direct detection rate, event rate with a light mediator case. And we found the non-zero direct detection rate can be obtained in this case. And some parameter space can be checked by future direct detection experiments like xenon n-ton. And another important point is energy spectrum of Pngb dark matter can be different from normal WIMP case. So this can be used to discriminate Pngb dark matter from the other WIMP dark matter model. So that's all. Thank you.
Thank you very much for nice talk. So it's time for a question. If you have any question or comment, please go on.
I have a questions.
Mm-hmm.
So first, so what is the motivation to consider light H2 in the second part of the talk?
I mean, because once we construct the UV completion of the model, we can expect naively dark matter mass can be larger than the MH2. because the level of phi is much larger than S. So that's why we consider this case.
The MH2 could be weak scale greater than 200 MeV. So why you are considering some narrow range of dark Higgs masses between 20 MeV and 200 MeV?
Yeah, because we wanted to discuss the direct detection rate because if sensitivity
on this, I see.
Yeah. If you consider heavy MH2, you cannot get any event rate.
You want to see, I see, some interesting shape, I see. And another question is when you have a light H2, this light mediator could give rise to Sommerfeld enhancement for the dark matter annihilation, right? So have you checked that? I mean, because it could enhance also this dark matter annihilation cross section significantly at low velocity.
Yeah, actually, I remember I checked. Actually, in this model, there's no Sommerfeld effect because of the nature of Pngb. I mean, if you need to calculate radar diagrams, right? Mediated by H1, a lot of H1, H2. And then that is similar to this structure. So in this case, I mean, there's no long range interaction for Pngb dark matter. That is highly suppressed by small momentum of dark matter.
I see.
So that's why.
I see. Okay. That is interesting. Yeah. Okay, I see. Okay.
Is there any other question or comment?
I have the go ahead. Please go ahead.
Takashi,
you can go ahead.
I've got it. Very simple question. Why did you choose the document velocity in this slide as 200 kilometers per second?
This is a typical value of dark matter velocity, and in fact, dark matter velocity there is a distribution called the Maxwell-Boltzmann distribution. In our calculation, we took into account here F this is a Maxwell-Boltzmann distribution for dark matter velocity. So 200, this one is a typical value of the dark matter velocity. Just one example.
I've got it. Thank you.
May I ask that the energy spectrum difference between the pseudo-Nambu-Goldstone boson and WIMP was interesting. So does the energy spectrum also depend on the spin of the dark matter? Because the propagator structure should be different.
Spin.
Not the propagator. Maybe spin of the mediator or anyway, spin of the dark matter or spin of the mediator, it depends on.
Let me see. Yeah, it could be because depending on spin of dark matter, the cross section, the shape of the cross section can be different. So, but I don't know.
In this case, you have a scalar, and Goldstone is a scalar dark matter.
Yeah.
Maybe Kimiko was asking about the spin dependence of this energy spectrum. But for instance, for WIMP dark matter, with a similar mediator.
Yeah, probably there's a similar, there's a small dependence on spin, dark matter spin, I think, but not so different, I think. Yeah, basically, independently on spin of dark matter, you can have this dotted green line like this. And sorry, I don't know. Yeah, sorry.
Thank you very much. Also, maybe.
Can you show us the efficiency plot from John? It is interesting to see you have a very large momentum, large events in the low energy.
Yeah.
But it is kind of cut off due to the efficiency, right? Here, the black line is the black line is the efficiency.
Yeah.
I see. So you have a very small efficiency. I see. So this is the nuclear recoil, right?
Yes.
For electronic recoil, it should be there must be similar plot for electron recoil, right? Recently, there's some general one-tone electron recoil excess. So what if you have electron scattering? But the WIMP case is not that important. But
I don't know, for electron recoil case, maybe the detector efficiency is much different. Maybe I don't know, because experimental techniques are different. I think.
So with the same similar mediator, but the electron, you have a small recoil. Otherwise, unless you have an elastic scattering. Okay. Yeah. So I think the IC indirect detection bound is very strong in this model. Right.
Yeah.
Instead of direct detection, of course, if you have a light mediator, as you said, there's the enhancement in the form factor.
Yeah.
We have a strong constraint, but the light mediator is not necessary for me. So still, I think your model looks good with a direct detection.
Thank you.
Yeah.
Thank you.
But for indirect detection, it looks like there is no velocity suppression.
For indirect detection.
For indirect detection.
No suppression.
Right. Yeah. Okay. Yeah. This is the prediction of this model. So just to you have the same channel for direct detection and indirect detection. But one for direct detection, you have a suppression. For indirect detection, you have no suppression. Actually, this reminds me of our paper in our group. So we consider pseudo scalar mediator. And typically pseudo scalar mediator, you have a suppression, velocity suppression in the direct detection, but there is no suppression in the indirect detection. So yeah, it looks.
You mean fermionic dark matter.
Yeah, if the dark matter is fermionic, yes.
Yeah. Yeah, that's another option. Yeah.
Yeah.
I know some papers.
Yeah. So
Mm.
the pseudo-scalar mediator or pseudo-scalar dark matter might be important ingredient in your case.
Yeah.
Some other cases.
Yeah.
So okay. So
other question or comment?
So I have a last question on the domain wall problem. I just you mentioned this, but I couldn't pay attention to this. So what was the conclusion? You don't have a domain wall problem?
I mean, basically in this model, simple model, we have a domain wall problem, but this model, the domain wall problem can be solved by considering some possibilities, like UV completion. Because the original model.
Yeah, without modifying, without modification, you have a domain wall problem.
I mean, at high energy scale, we need to modify.
You need to modify it. So can you show us what are the solutions? UV completion, I see, low energy.
Yeah.
I see. So this is because of the G2 breaking minimum.
Yeah.
Okay.
Sorry, may I ask some introduction part? In the indirect detection, you told us that the final, BB and tau final state is important. So I was wondering why B and tau, not electron, not muon, not charm, BB and tau.
Yeah, you can also consider different channels, but in particular, these BB bar and tau, these are much stronger than the other channels because a lot of gamma rays are emitted after this tau and B decays. So that's why.
I see. And you consider the electron positron pair because the H2 is enough smaller mass.
Yeah.
Because of that, you didn't think this channel.
Yeah, because H2 dominantly decay into E plus minus in our parameter setup.
Yeah. Very small mass.
Yeah.
Thank you very much.
So that's why in this case, Fermi-Rat gamma ray observation, this boundary is not so strong. If you consider tau, for example, this gamma ray, the blue line go down around here. So, yeah.
Oh, I see. Thank you very much.
Okay, so if there is no further question, let's thank Toma-san. Thank you very much.
Thank you very much.
Okay, thank you. Thank you very much for your nice talk.
Thank you.